All right, so in this video, we're going to be covering Visor Finance, $8.2 million, and happened roughly last year. And we're going to step it up by actually seeing not only how they exploited the protocol, but how they actually dumped their exploit into Uniswap to get ETH in return. So just like last video, we're going to actually be forking the blockchain at that exact moment in time and deploying an attacker contract that actually exploits the protocol exactly how the attacker did it, because that most realistically shows what actually happened, and we can get a better idea about what's happening in these hacks. All right, so let's look at what exactly happened. It allowed certain contracts to mint unlimited rewards. So this was the hacker's address. So let's look at what they actually did. Let's look at all their transactions. So it looks like they deployed a contract that actually was in charge of exploiting the protocol. They approved Uniswap to actually trade their exploit tokens to ETH so they could actually cash out. They did so using the swap exact tokens for ETH method. And they also interacted with Visor itself to actually exploit its vulnerability. So let's look at the reward contract they actually exploited. Now it says a vulnerable require check allowed them to mint unlimited shares using their own contract. So let's look at deposit and see what that vulnerable require check was. So right here it says it's vulnerable. So basically what it's showing is that the intention of this contract was to say, hey, look, if I'm a user and I'm depositing funds, I want to deposit this many funds, then it's going to calculate based off of some formula, based off how much I deposited, and then it's going to mint me that appropriate token share back. But what it didn't really realize was that, so what it wanted was that this if condition was only going to be entered if the admin was calling this function, right? It says if the owner of this contract is the message.sender, then do this action, otherwise do this action. But the interface at which iVisor implements is not actually this contract itself. As we see, the from parameter is controllable, so we can pass in our own from parameter, and then the owner check will actually could be on a contract we deployed. So as long as we deploy a contract with the owner method that returns the message.sender, this require check is going to be passed. So therefore, this is not sufficient as a form of access control, and ordinary users can actually get into this if clause, which ideally should only be protected by an admin. So it also looks like this iVisor interface implements this delegated transfer ERC20. So all we need to do is make sure that our attacker contract implements this method and that it doesn't revert, so we can get past this if condition, and then it'll mint us our appropriate shares. So if you actually look at the else clause, if you're not technically an admin, which we showed doesn't work anyways, it would transfer the amount of money that you chose to deposit, so therefore there'd be no way to mint unlimited shares. But it does not do that if it thinks you're the admin, so that's where the exploit lies. So as usual, we're going to be using Foundry to actually reproduce the exploit. So what we're going to need to do is gather all the ABIs and the interfaces of the relevant contracts we want to interact with, and we also need the contract addresses of the rewards hypervisor, because that's what we're going to be interacting with. So what we're going to do is first, because we're actually going to be interacting with Uniswap, we need the Uniswap v2 interface as well. So we can go to the attacker's transaction and see everything they interacted with and get that information from there. So we need the Uniswap v2 router interface, and we also need the interface of the reward contract that got exploited. So we can go to the ABI. This mouse is a little fucked up. All right. There we go. ABI to Sol. And we can paste that there, and we can get an interface, and we can call it like Visor interface, and then and copy and paste that here. And we can also do that with the Uniswap v2 router. So we can get the ABI, just like we always do, copy that here. Where is it? Here, copy it here, paste it in here, and then we'll get that interface, and then you copy and paste it in this file. So now that we have our two interfaces, we need the contract addresses of what actually got exploited. So rewards hypervisor is at this address, C9F. So in our test, and our setup function, which is our constructor, we're going to actually we're going to copy and paste that address, and then Uniswap router is at 7A2. So we've copied and pasted that as well. So now we can interact with both of these contracts. And as if you recall from the last video, we actually set the block number at which, was the exact point in time at which this contract got exploited in the run command itself. But we can actually do that within Foundry itself using a VM cheat code called roll fork. So this is actually going to set the Ethereum chain back to this exact block number. And it's a little easier to do it this way. So we're going to be doing it like that. All right, so now let's actually go through how this attack actually happened. So in source, we kind of set up everything we need for our test to actually run, and our test is actually going to deploy everything that's relevant and actually execute the attack. So we have the Uniswap v2 interface imported in our test, which actually just gives our Uniswap v2 contract the exact methods that can be called on it. And then we do the same with our Visor contract. We supplied an interface so that when we reference the contract here, we know what exact methods can be called on Visor contract. So in our last video, we actually set the block in the run command itself, but here we can actually do that with a Foundry. So the point in time at which the attack actually happened can be set within our constructor so that we can do it there, and it's a lot simpler from just doing it from the command line. So if we look at what actually happens in our setup function, it changes the block to the point in time of the hack. It gets references to the Visor interface, which is the rewards hypervisor contract, and it gets references to the Uniswap v2 interface that was in which the funds were routed to, so that we can interact with that as well. We also deploy our malicious contract, and then in our test visor, we actually run the exploit. So let's go through line by line what exactly happens. So in test visor, what it's going to do is it's going to print our ETH balance before the hack. Then what it's going to do is it's going to interact with that the incorrectly implemented deposit function, and it's going to actually set the from address, as we recall over here. If it can pull up. It's going to actually set the from address to the malicious contract that we deploy. So if we look at the second parameter, which is from, it's going to be the contract that we deploy here. Then it's going to withdraw the money, which actually converts the minted shares we have from vVisor to Visor, but we're going to go in depth in that in a second. So let's actually look at what our exploit contract is doing. So basically what we said was that that owner method just has to match message.sender. So we're interacting with this as if we're address 7. So as long as owner address 7 matches the address that's sending the transaction, which we've told Foundry to set our address to 7. If you were to interact with this contract on an EOA, it'd be whatever address you set. But because we're replicating in a test, we can just set it ourselves. So as long as 7 matches 7, which we've implemented, then that required check gets passed. Now, in addition, we have to make sure that this method doesn't revert, or else we won't be able to mint our shares. So basically, we just have to implement a delegated ERC20 transfer method that takes 2 addresses and an uint 256 and make sure that it doesn't revert, so it doesn't require any implementation. From there, we get minted from there, this if condition gets passed, and then it's going to mint us our shares, so we can actually see that, or maybe we should put a console.log of what actually is our vVisor balance after deposit. And what we're going to see is vVisor token dot balance of, and then we'll say our address of OX7. So now if we actually run this exploit, we can see what happens. So after balance, wow, we got minted a massive amount of tokens, and we didn't give this contract anything. So basically, we just minted ourselves a bunch of free tokens, but there's still some more steps after that to actually withdraw this into a profit. So we need to call the withdraw method, which actually is going to convert our vVisor back into Visor, and we need Visor. So if we saw we got minted vVisor, we need Visor instead, because Visor is the Uniswap, Visor to ETH is the Uniswap pool that exists, and in order to interact with that pool and cash out to ETH, we need Visor. So in order to turn our vVisor that we got minted into Visor, we call the withdraw method. It's going to actually burn our vVisor, and it's going to transfer you the rewards you get based on how much vvisor you withdraw. So we're going to withdraw our total balance, so exact amount of vvisor we got minted, and we're going to say give the rewards to address 7. Then, well, after all the rewards, we're going to set up Uniswap to actually trade our Visor to ETH, so we can actually get the amount of ETH that can be traded for that amount of Visor. Interacted with what looks like Uniswap v2 router 02. So if we actually go to Uniswap and we go to v2, we can actually go to that router and see how this method, which then actually perform the swap exact tokens for ETH, works. So if we go to smart contracts, we go to the router, and we see swap exact tokens for ETH. So let's see how this exactly works. Where'd it go? It takes the amount of tokens to send, how much you want to receive for it not to revert, the path of tokens, so basically what tokens we want to trade for, who should receive the ETH, and it's going to return basically what was the trade. So how much did you trade and how much ETH did you get back? So in code, that looks like we want to trade. Amount in will be the exact amount of balance we have of Visor, because we want to cash out everything we have. The amount out minimum is 0. So that's not going to actually give us 0 back. We're just going to say, hey, give us all that you can, and we want to just cash out everything. Now we actually have to set up a path. So it says the path of the first input token is a token you want to trade. The last must be WETH. So at path 0, we set the address of Visor token. At path 1, we set WETH. Then it says the recipient, or the 2, so it's going to be the recipient of the ETH. We want that to be address 7 because that's where we want the funds to last. And then it says the Unix timestamp, the deadline at which the transaction will revert. So I just set some random timestamp to make sure that it's far in the future so that our transaction doesn't revert. Then it's going to give us how much tokens we got back, so it's going to give us the output of the swap, and we're just going to print that out to see how much ETH we actually got. And real quickly, before we did all that, we actually had to approve Uniswap to trade our Visor, so it had permission to actually do so. So if we actually put everything together, we run the hack, we can see that we had 1, and this is scaled to, this actually wasn't even scaled to 1 to the power 18. So we basically had 0 ETH before the hack. After the hack, we had a shit ton of vvisor, and then post-hack, we traded this much amount of Visor. So vvisor got converted into Visor, and we traded that amount of Visor for 60 ETH. So as we saw in the Rect News thing, while a bunch of tokens got stolen, cashing out wasn't very profitable. So they lost 87%. We got 60 ETH. At the time, ETH was trading for about maybe 5K. So this was a 300K hack. A lot more money got burned, but overall it was actually relatively simple in comparison to what actually got exploited. In reality, all that we needed to do was make sure that the owner method was implemented that returned the address of message.sender, and that this method didn't get reverted. Oh, and real quickly, we also needed this receive method because this contract had to receive ETH. It needed permissions to be able to receive ETH, so we had to make sure that that receive method was there. So there we go. That was the end-to-end explanation about how this hack exactly happened. So in summary, that malicious or that. So there we go. This is about an end-to-end proof of concept about how this exact happened, and it's probably exactly similar to how the attacker actually implemented this. So that deposit function had a bad require statement that didn't check if the owner was right, which allowed us to mint a bunch of vvisor. Then we cashed out that vvisor with this withdraw statement and then converted that to Visor. And then from converting that to Visor, we approved Uniswap to trade that, and we traded our Visor to ETH, in which we amounted to a total of 60 ETH after everything.